Hello and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at ICSE, as well as keynote speakers and distinguished paper authors. I'm Shane McIntosh. I'm an assistant professor at McGill University, and it's my pleasure to welcome you today. Before we get started, there are a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you'll find a number of additional widgets and resources to help you interact with the webinar experience. If you are experiencing problems with the slides or audio, just press the F5 key on Windows, Command R on a Mac, or refresh the browser on mobile devices, or you can close and relaunch the presentation. To control the volume, adjust the master volume on your computer. If you have any questions during this webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. At the end of the presentation, we will have time to respond to your questions. This session is being recorded and will be archived. You'll receive an automatic email notification when it becomes available. Okay, so today's presentation is What Role for Programmers in the Age of AI, and it's going to be presented by Tim Menzies. So Professor Tim Menzies is an IEEE Fellow and a full professor in computer science at North Carolina State University, where he teaches software engineering, automated software engineering, and foundations of software science. He is the director of the RAISE Lab, so that's Real World AI for Software Engineers, that explores software engineering, data mining, AI, search-based SE, and open access science. He's the author of over 250 refereed publications, the editor of 3 recent books that summarize the state-of-the-art in software analytics. In his career, he's been a lead researcher on projects for NSF, NIJ, DoD, NASA, USDA, as well as joint research work with private companies. Prof. Menzies is also co-founder of the Promise Conference series devoted to reproducible experiments in software engineering. He's an associate editor of TSE, TOSEM, Empirical Software Engineering, Automated Software Engineering Journal, and many more. It's my pleasure to introduce Tim. So, Tim, without further ado, take it away.
Thanks, Shane, for that introduction. Thank you to the ACM for the invitation to talk today. One minor clarification, I'm currently not an associate editor for TSE. Just one minor correction to Shane's otherwise fantastic introduction. I want to talk about what AI means for software engineering. I want to try and give you some idea that AI will not replace software engineers. It will just give us much more to do. I want to say that something called programmers do much more than programming. So even if we replace what we call programming with AI methods, we're still not going to replace programmers. I characterize software engineering as the search for feedback, and I think that it's going to be a human engineering task to come up with innovative combinations of our AI building blocks into new higher level structures. We'll talk about some of those building blocks today, something I call Duo, data miners using and used by optimizers. And what you'll see when I present it is you'll see lots of things that can be automated. And I'll say, yes, once we start using Duo, data mining, using and used by optimizers, for a couple of years, we're going to work out ways to make all that automated as subroutines, at which point we'll have building blocks for the next generation of even more complex software, which human engineers will be required to handle and manage and maintain. So I want to say that we have an engineering challenge. We have a lot of advantages with AI, a lot more building blocks we can put together. And some of these building blocks can be auto-configured, but the range of possible combinations is so interesting and so nuanced that we still need human ingenuity to do our AI and software engineering combinations. So humans are still required to make the AI make sense. I want to say that what we have right now with our fantastic results from artificial intelligence is that software engineers now have many more building blocks, many more items in the buffet they can order when they configure, they build their software systems. And I think this huge buffet of options requires expertise to use correctly. If you go to any restaurant, there are many things to be bought from the menu of the restaurant, but there are connoisseurs, there are waiters that can tell you the best combination, the way we can mix and match the best food that is most suited to you. And in this talk, we're going to talk about a thing called Duo, which is data mining using and used by optimizers as an example of the ways to configure these methods. I want to really stress at this point that Duo, data miners using and used by optimizers, is only one way to configure all these wonderful AI building blocks. And there's a tremendous space for human ingenuity to find fantastic ways to configure these things. As Shane was kind enough to point out, I'm from North Carolina State University. My website is menzies.us, where you can find out more about me. My lab is Real-World Artificial Intelligence for Software Engineering, and we talk about not just how AI can be applied to software engineering, but also, and you'll hear much of this in this talk, how software engineering can be applied to AI. So it's SE for AI for SE. The material you're going to hear today, if you want more details about it, please look at this paper here. The talk I'm giving you now was co-written with Leandro Minku, Amrit Agrawal, Ji Yu, Hu Tu, Marcus Wagner, and this was presented at the Foundations of Software Engineering Work Conference in 2018, and then we went away and wrote a paper summarizing our ideas. So if you want to read more about this, there's a URL there on page 6. I invite you to read that. So I want to talk about why I want to talk about expanding this idea of programming above programmers. I want to talk about why I'm interested in combinations of AI building blocks by humans, and that'll take us to this thing called Duo, data mining using and used by optimizers. So at FSC, we had an absolutely fantastic talk where Eric Mayer talked about all the things you can do to automatically configure code. And he characterized software 1.0 as a process where humans and coffee get together to make code. And he talked about a software 2.0 process where the humans specify the high-level goal, the what, and then AI agents work out the how. And his talk is absolutely brilliant. If you want to find a reason for learning Scala and automatic composition and formal methods, read his talk. It's an amazing thing. But I will take issue with his definition of programming and programmers. It seems to me that AI won't replace programmers because there's still much space for human, novel creativity. Programmers do much more than just program. Programmers don't just sit in some back room, filling in the details to a specification provided by someone else. Programming is the core thing inside software engineering, and to me, software engineering is the search for feedback on ideas, assessing what to do next, what was a good idea, what's ignorable. The chart on the right-hand side shows the number of open and closed issues at GitHub at various days of the week, and GitHub is a large open source repository. And the key feature to note from this figure is that usually there are more issues opened than closed in GitHub. When people use software, they come up with more requests for change than what anyone can ever handle. Which means that between the large gap between proposed things to do, the large blue open issues, and what we actually do, the red closed issues, some human has to negotiate what should be done, what shouldn't be done, what bugs can be ignored, and this is essentially a human task. Now, there's lots of automation we can use to help in that process, but it's humans plus automation together that I think is the future of software engineering, and I don't think that can be 100% replaced or even 50% replaced with AI. There are things humans do just much better than AI. One of them is they provide trust and they rush in to help when systems fail. Recently, I changed my cell phone provider because I had the experience of ringing up my old provider asking for help, and I got someone that was less than skilled on the line. And I realized that one reason I want humans involved in my system construction is when the system starts failing, there's a target team that can run in and do things, humans. And I think there's lots of things humans can do which I'm yet to see good ways to do with AIs. Supposing that we want to define the high-level goals of some project, problem definition. Supposing we're doing very complex data collection and we run into the area where there's data we want and we can't quite get. So someone creatively points out that this variable and that variable are kind of surrogates that can stand in for something else. That level of human expertise, that understanding of the data model, I don't know how to automate that. And there's also, I think humans have a real role in managing organizational impact. Supposing you can reduce the testing time for some system by a factor of half, and you no longer have to test things overnight in a long regression run, but you can do lots of small tests during the day. That means you can release more often during the day, which has impacts on how you organize your organization. It has impacts on what your customer sees from you, how quickly you can respond to customer issues. That has organizational impacts that humans, the programmers, have to be involved with to manage. So I don't think the right thing to do with all the options we're seeing now with modern AI is to take all this fantastic space of options and throw them into a blender and just put them on the cloud and run them in some massive CPU experiment. We're already seeing too much blending of complex issues. One of my grad students went to Google for summer, and he did all this work where he was using 3 years of CPU per day to do his work at Google. And there's lots of other examples where people are using decades of cloud-based CPU to run through very large spaces of options. And to me, this is just not something that's good for science. We lose repeatability. If no one else can repeat the experiments outside of the people that run the cloud environments, or no one has the dollars to buy the cloud environments, this is just the wrong way to do things. I want to see more nuanced, clever ways of combining all the new tools we're getting from AI. Now, some people want to get humans out of the loop totally. Dijkstra famously said in 1979 that the notions of users cannot be precisely defined, and therefore humans have no place in computer science or software engineering. And I had colleagues I went to university with who really said that the goal of machine learning is to kill human experts and resurrect them with dead ones. And I do not hold with the right-hand side view. Some of my best friends are humans. What I think is more true is that, and despite what Dijkstra said, I think humans can be defined mathematically. I think humans are the force that shapes the goal space. And I think engineering is surfing the goal space. And I think software engineering is building and using software that surfs that goal space. And if you want to know what I mean by that goal space, here are some representations of that. If you look at the objective space of any complex multi-objective problem, you get things like the purple curve shown left. And when you look at the interactions between all the objectives, we find valleys and cliffs, and you might be able to see a little black dashed arrow trying to walk its way around the purple region. And that's my characterization of anyone exploring a space of options. Bottom left, you can see the usual diagram used to describe a neural network trying to minimize the errors associated with its thinking as it seeks the minimum error at the bottom. And this device surfs the error curve to come up with a model for you. And if it goes too slowly in its surfing, it gets stuck in the local minima. If it goes too fast, it'll whiz past the global minima and you'll never see anything useful. And on the right-hand side is the wonderful example of branch rabbits that over time evolve over a landscape. And these landscapes aren't longitude and latitude. They're decisions within the rabbit's genome. And so top right, you can see a case where there's an obvious best place to evolve to, and the rabbits go there. And bottom right, you can see a landscape that's basically flat. So the rabbits evolve multiple possible solutions. So you might say that's not software engineering. And I say, well, times change. People have often said that something isn't software engineering, and later on it was. Dijkstra in 1979 said that software engineering was not about users. And I don't think that's an idea anyone would accept today. The clean room people in 1985 literally took away the compilers from programmers and said, programming is not about testing. Programmers should write provably correct code, and then a separate team will do the testing. And I don't think anyone these days accepts this separation of programming and testing. And then as late as even up to the 1990s, there were prominent publications saying that software engineering is not about requirements. Requirements happen elsewhere, and we do the software engineering afterwards. And I don't think anyone that is interested in continuous deployment or agile would want to accept the idea that they should ignore requirements these days. Software engineering used to not be about deployments, and now our continuous integration people have taught us the benefits of integrating deployment and operations. And a lot of my colleagues say that some of the things I'm talking about isn't about AI, and I reply, software engineering, AI is still software. AI software is software that must be maintained, validated, interfaced. We need usability additions. So AI certainly needs software engineering. Now, I want to give some examples of how, I want to make this specific. So now we go from very high-level, business-level motivation into some examples of what happens when you take AI building blocks and put them together. And the building blocks I'll particularly explore are optimizers and data miners. And this is not to say this is the only way to combine AI building blocks. There's so much interesting work in AI right now. There's so many interesting building blocks that could be put together. I'm just going to offer some details on Duo, data miners using and used by optimizers. Now, this idea of Duo, if you know the literature, it comes from, it's the intersection between two fields. Something's called search-based software engineering and something else called software analytics. And one of these communities deals with a lot of data mining, and another one of these communities deals with a lot of optimizers. And I say best results come from putting these two sets of ideas together. And I better define some things before we go on. I better define data mining. I better define optimization. And I better define something called hyperparameter optimization. And so data mining is learning patterns from data. The data miner tells you what is. So we could learn, say, a decision tree that could tell you with this combination of observables, you might have this probability of a defect. And if you can see it on this screen, there is a branch down to an orange conclusion, second from the bottom, labeled current branch. And if you fall down that branch, you have a prediction of 100%, that you will have a defect in your code. And that's what a data miner can give you. It tells you the shape of what is. An optimizer is about trends in the data. It tells you what to do. So, for example, if you have the same example with the same decision tree, there might be a nearby branch. Can you see desired branch with a probability of defect prediction of 0? And you might say, I'm going to plan to change my software such that I go from where I don't want to be, the current branch with a high probability of defects, to another branch with a low probability of defects. Now, this change, this delta, isn't necessarily going to work. This is a probabilistic, not a causal inference, but it's guidance that might work. And I can tell you in usual practice, this is a very useful guidance to follow. Now, building these trees themselves has a whole bunch of options. Hyperparameter optimization is the black art of tuning the control parameters for these decision trees, you know, how deep the trees go, how you divide the numerics. And every learner, not just decision trees, have got magic tuning variables. And one of the interesting things Duo can do is if we apply optimizers to data miners, we can learn the best tuning parameters for particular domains. Now, data mining and optimization have a very deep connection. So if we take a black box called an optimizer and break it up, we'll see something. And if we take a black box called a data miner and break it up, we'll see something. And what the next couple of slides try to suggest to us is that if we do that breakup, we will see basically the same thing inside a black box that one person calls an optimizer and what another person calls a data miner. So just look for the similarities of the internal structures in the next couple of slides. So let's hit the optimizer with a hammer, and inside what we see is a response surface. The optimizer has tried to discover the shape of options and how it affects objectives. And what the optimizer suggests to you is it says put on a set of skis and go that way down the slope. So the optimizer finds the landscape and gives you a pointer saying go that way. Whereas, and so, for example, if you're trying to do project management and you want to minimize duration and maximize profit, you might come up with a bunch of random ways to configure your project, and your optimizer might look at it and say, a lot of these are rubbish, but here are the better ones, and that's the green curve. You might say, thanks, optimizer, can we now surf along the response curve to get a better thing? And the optimizer might say, okay, I'll now combine things from the green curve, a lot of other options. Here's the best we've found. That's the red curve. And you say, thanks, that was great. Can we do it again? And so we might find lots of options on the red curve, combine them in an interesting way, and we get the blue curve. So that's optimizing to achieve some desired goal. And of course, the desired goal here is top left, maximum profit, minimum time to develop the code. Now, if we take a hammer and break up a data miner and look inside, we will see the same internal structures and we will see the same internal reasoning. So if we take our hammer and hit the box, we find again a response surface inside. And whereas before the optimizer said, here's a set of skis, here's a direction, go that way, what the data miner will do is take a pair of scissors and cut up the response surface and say, over here you've got oranges and over here you've got apples. But if we ask how the data miner does its work internally, we will see a process that looks very much like the optimization process we saw before. So supposing you have a range of ways to configure a data miner, this is the hyperparameter optimization problem. And you try a bunch of random ones and you get the green curve, and that looks good. So you say, let's try combining some of these. Oh, that gets us to the red curve, and that looks pretty good. And let's combine them to the blue curve. That looks even better. And we know it's better because we're surfing a response surface, trying to get to the point of minimum false alarms and maximum recall, which is the heaven point top left. So what I hope I've shown you here is that, and this connection between optimization and data mining holds not just for numeric optimization, but also discrete optimization. If you look at what happens inside a neural network, which is supposedly a classifier or a regression device, there's a lot of optimization happening inside the neural net. Bottom left, we saw this diagram before, where the neural net is trying to adjust its internal weights to reduce the difference between predicted and actual, try to reduce its error. And as the neural net does its work, it's sounding like an optimization process. It's trying to, as quick as it can, get to the error, but not go so quick that it just keeps jumping over the best and lowest error, and not so slow that it gets stuck in the local maxima. And this sort of picture of learning as optimization also holds for discrete learning. If you ask me to build a discrete rule, a classifier for all the Australians on this phone call right now, in this seminar right now, if we just built a learner that says Australian if true, then that would correctly grab all the positive examples shown on the y-axis of Australians involved in this seminar. But we'll access a lot of non-Australians, a lot of people from other countries on this webinar right now, and that's the non-Australian examples on the x-axis, the negative examples. Now we might say let's avoid all the false alarms by saying Australian if false, and that gets us to the model bottom left, which has the benefit of no false alarms. No one who's not an Australian will be tagged as an Australian, but it also means we don't find any Australians at all. We get very low recalls. And if we walk the space between these two extremes and we come up with rules that use one condition like A, or two conditions like A and B, or three conditions like A, B, and C, can you see we're walking kind of a response curve? And as we combine these different rules to get better curves, we're sort of doing like the optimization process we saw in the last couple of slides. So that's a statement that data mining and optimizing have very close associations. Now, if that was really true, then we should test that idea. There should be lots of examples of people using data mining and optimization put together. So we did a literature review looking exactly for that effect. In the software engineering literature, are there examples of people combining data mining and optimization? So this is the report put together with my co-authors, for which I thank their hard work. And this report we're talking about is shown on the PDF shown at right, and that's available for free download. So the way we did the literature review is we searched for terms like software engineering and optimization or evolutionary algorithms, or data mining or analytics or machine learning. And we searched inside some online repositories of papers, Google, IEEE Explorer, ACM Digital Library, and that found 393 papers. And then we said, let's just cull them to recent papers with at least 10 citations per year, or they're just most recent, last 2 years. And it turns out that IEEE Explorer and ACM are much more conservative when they assign citations. So 10 citations a year in Google is about 3 citations a year in IEEE Explorer and ACM. And when we apply that, our 393 papers came down to 90. When we read them to confirm that we're doing software engineering applications, that took us down to 72 papers. And when we asked for data mining and optimization, we found 30 papers. There was then a consistency check where we shared the results with each other. And what we found was the papers on the next 3 slides. So what we have here are 30 examples of highly cited papers in the recent literature putting together data mining and optimization. And that's suggestive but not total confirmation that there is an interesting engineering combination of data mining and optimization. And I offer this to you people as an example of the kind of things that happen when we take AI building blocks and put them together to make a new structure. And we're going to talk about what we found with that. But just to repeat the message said at the beginning, yes, in a couple of years' time, we'll know how to automate a lot of these connections, but then we'll have new primitive building blocks, which I predict the next generation of human software engineers will look at and say, well, with those as building blocks, we'll now build a bigger structure on top. So the humans will always be there involved in software engineering, even when there's AI involved. With the literature review we asked what was the optimizer the data miner used, how was it applied, what domain was it in, what problem did it address, and what's the take-home message of that particular work. And we found all sorts of problem areas. And this list is worth reflecting on because this is what programmers do. This is what software engineering researchers do. These are the sort of tasks I'm often asked to do when I do industrial data mining, things like project management requirements, design, looking for security. And all of these can be explored with some degree of automatic involvement. Project management is the search through options to find out what things affect effort, and that can certainly be automated. Requirements is certainly the exploration of complex competing goals and complex architectural decisions. Design is certainly the extraction of products from a very large background space of possibilities. And there's a lot of automation involved that could usefully be deployed for all these things. But the main thing is, unless you've got a human in the loop guiding and assessing, all that automatic computation will be wasted. Project management is the quintessential human exercise. I don't know how you can do project management without humans talking to humans. And so there's many things on this list where we found people doing data mining and optimization. And when people say we can replace programmers with AI, just give them this list and say which of these tasks can be 100% replaced by AI, or 50% replaced by AI, or 20% replaced by AI. Now, you might say that this is not programming. You might say what's on here is not software engineering, it's something else. It's management or analysis. And I'm saying, no. If you're talking continuous deployment, if you're talking giving everyone authority to work at all levels of software and everyone being able to contribute to the overall health of a project, everyone called a programmer is involved, has something to contribute to all these items. Now, the tools used in these things are things like decision trees, support vector machines, instance-based reasoning, ensemble learning, Bayesian methods, regression neural nets, etc., etc. And these are the years we saw them. I can't fit a regression line to this and say things are improving at R squared 0.7, but what I can say, it's being used more and more. So I would say to software engineers, make sure you know what all these things are, because these are the building blocks you'll be asked in the near future to incorporate into your designs to make those designs better. And in terms of optimizers, again, these are the years where these optimizers are used. And again, I can't fit a regression line through them all, but I can say they're being used more and more in recent times. And then, let's ask our current generation of software engineers, how much do they know about genetic algorithms, or GAs? How much do they know about DE, or differential evolution? Just as an aside, if you want to get into optimization, differential evolution is an incredibly simple, very fast method. If I explained it to you, you could build your own DE device in about half an hour. NSGA2 is a very popular genetic algorithm. PSO is particle swarm optimization, genetic programming, and when you get down to the lower numbers, SWAY, Flash, these are particular products from particular research labs. But then I asked my SE colleagues, do you know about these tools? I'm saying you really should, because these are the things you could use as new building blocks to significantly extend your systems. Now, what can you do with these building blocks when you put them together? In our literature review, we found 4 flavors of data miners using and used by optimizers. And those 4 flavors are here. You know, the data miner is the optimizer controls the data miner controls the optimizer, or there's some dancing with both, with the data miner and optimizer, you know, each hand off to the other things and get things back. And we'll talk about these. Let's talk about data mining, control, and the optimizer. So here's an example from software engineering. We're doing text mining. We're going to the Stack Overflow question and answer site, and we're asking what questions are like other questions in the Stack Overflow. Now, we had a baseline result from a deep learning application, and we asked ourselves, could we do better than the deep learning result? And we found that if we applied that optimizer called differential evolution to tune the parameters of a support vector machine, and as you recall, a support vector machine generates extra dimensions to find better ways to separate examples, and to generate those better dimensions, it uses what's called a kernel, and the kernel has magic parameters, and the differential evolution device found it. Now, when we found we could get results equivalent to the deep learner using differential evolution applied to support vector machines, but it was crazy slow. It took a long time. So we took all the configurations and we clustered them using the k-means clusterer, and then we ran our differential evolution per cluster. And even with all the overhead of differential evolution, and even with all the overhead of clustering, this rig ran 500 times faster than the neural network to achieve equivalent results. And in fact, that was 500 times faster using one processor on one laptop. If we used all 8 processors on one laptop, we were 1,000 times faster than a deep learner. This is a very nice example of how you can very easily combine AI building blocks to have tremendous improvements in your system. That was an example of a data miner controlling the optimizer. The data miner, the k-means clusterer, divided the problem up into lots of tiny problems, which meant the optimizer could run much faster. Reversing it, we'll now have the optimizer controlling the data miner. So Shane McIntosh's group at Canada did a lot of stuff on this, and one of their interesting results, and I really should ask Shane if he has comments on this at the end of the talk, because I think he was actually involved in this paper, is that they used an optimizer to pick parameters for data miners. And here you can see dozens of data miners being applied to lots of different data sets. The y-axis on this graph is some measure of goodness, and higher is better. Now, this graph, what's really interesting to look at are the blue circles sitting on the x-axis near the bottom. So you can see there's a blue circle on the very left-hand side at the bottom, and it's labeled C5.0. And this is a learner which, before it was tuned, ran very, very badly. And you can see some other blue circles sitting on the x-axis showing you very bad performance of a learner before it was applied to it, before it was tuned. Now, the red shows the results after tuning was applied, and you can see that that very bad learner, called C5 on the very left-hand side, is now doing fantastic results. You can see its red performance curve across multiple different experiments. And so now I'm very worried about anyone that proposes a data mining result that doesn't use an optimizer, because, you know, we can see that using the optimizers in this way can significantly improve the performance of the data miners, and even things that look very unpromising before tuning can be superior and actually recommended after tuning. Another thing is dance with both. So at ICSI 2018, there was a great example where optimizers and data miners were put together, and this was to learn test cases for vision-based control systems for autonomous vehicles, which, as you can imagine, is a rather complex task. And so they did a fascinating interplay between an evolutionary algorithm and a decision tree algorithm, where the evolutionary algorithm would produce lots of solutions, and the decision tree algorithm would come up with ways to divide up that space, and then the evolutionary algorithm would work within those spaces and wouldn't oversample within one space and move to another. And there was a round robin between the evolutionary algorithm and the decision tree, refining the test cases. And this is an example of Duo of using both optimizers and data miners in a cyclic manner. And finally, there are examples where it's very hard to tell whether you're doing data mining or optimizing. And this next example shows you just how close data mining and optimization can be. So if you've got a very complex configuration problem, what we'd do is we'd create a whole bunch of random configurations, and we'd recursively cluster them using the following recursive two-means clustering. We would recursively find two distant points, and then we wouldn't evaluate all the possible configurations because that's too slow. We'd just evaluate the two most distant points. We'd then wipe out half the examples closest to the worst point and recurs on the rest. And what you get is, you can see the colors here on the right-hand side. These are the clusters of configuration space. And the red zone is very low on the objective score, so the z-axis is the objective score. We just ignore that. And the orange, consider that a blanket of solutions. And in the orange, there's one high corner. And we take the whole orange blanket of potential configurations and move them half the length of the orange blanket towards the high end. We do mass mutation. This is called GALE. And when we did that, we applied it to very complex models of, say, pilots landing aircraft in adverse conditions. And this was a software engineering application where we were exploring FAA requirements of how pilots should monitor their instruments, software instruments during landing. And if a pilot's flying a plane, there's a bunch of things you don't want to happen. And each of these bad things are one graph on the left-hand side. So top left, number of forgotten tasks. And then in the middle left, number of interrupted tasks. And at the bottom left, interrupted time. And then in the middle top, number of delayed actions. And then in the middle, there's delayed time. The y-axis is the ratio of how well you're doing compared to some randomly generated examples that we started with. So if you hit 50 on the y-axis, you're twice as good as the initial random sample at the beginning. And this thing I showed on the previous slide, a thing called GALE, and the x-axis shows number of evaluations required to get to some better place. And what you see is the thing called GALE, in dozens of evaluations, gets to a place just as good as what's achieved in thousands to 10,000s of evaluations using something called NSGA2 or SBA2, which are standard optimizers. The funny set of boxes on the right compare the number of evaluations required for GALE, NSGA2, and SBA2 to achieve the goals. And each square here is 250 evaluations. And so you can see, and each row is a different model. So the model on the left showing the pilot thing is the CDA model that's the second row of the structure on the right. So here we see across multiple models that the thing we call GALE with very few evaluations. Like if you look very closely, you can see the red smudge in the GALE column showing how many evaluations took to get somewhere, orders of magnitude better than the others. So what we say is it's really great for a data miner to use, for an optimizer to use a data miner. The data miner can divide the problem up into sub-problems. The optimizer can explore faster. And so we'll just jump ahead. Advantages of using Duo. I think it's really powerful to add optimization ideas into data miners. Optimization literature knows about multiple competing goals. They have words like Pareto frontier and domination of solutions. And these are very powerful design goals, which I found very useful in my research into adding into data miners. And I think it's great adding in a wider concept of goal into data miners, because standard data miners have a set of goals baked into them. Standard data miners run very fast because they're optimized for particular goals. For example, you might want to minimize entropy in the C4.5 decision tree learner. Now, what's nice about optimizers is they typically accept a arbitrary goal as input. So you can say, please search for anything. And these are called meta-heuristic searches because you can't guarantee that an optimizer will run fast and achieve fantastic results for any possible goal. But what I do know is that if so the optimizers can run much slower than the data miners because the data miners are highly optimized for one goal, whereas the optimizers are willing to explore multiple goals. But then another reason to add data miners into optimizers, one of them is speed. Optimizers can run much slower than data miners. But what I hope I've shown you here in this talk is that if we use some data mining tricks inside an optimizer, we can get back the speed that we want from the optimizers. Another thing that's really powerful about adding data mining concepts into optimizers is that we can start doing generalization across the space. One of the reasons that the IXME18 people use data miners in conjunction with their evolutionary algorithms is they could divide all their examples into regions. They no longer had single point solutions, but they had regions within which they could reason. So if you wanted to explain all the blue dots shown top left to a user, you could print out all the variables inside those blue dots and your users would be confused. If you put a decision tree on those blue dots, you get a structure that's what's shown on the right. And what you get is a whole bunch of statements like if A is greater than 0. Now what's really powerful about that is the decision tree is not giving you a point solution, it's giving you a volume within which a solution holds. And so while a point solution might be brittle, one tiny change means you lose all the advantage of that solution. A decision tree, a rule-based learner that marks out a volume, A greater than 0, is telling you, look, it doesn't matter if you're 10 or 11, that doesn't matter. What does matter is don't drop below 0. You'll have all the advantages. Now, besides speed and generalization, another thing data miners give to optimizers is this concept of trust. If I can build human-readable models from optimizers, then I can do things like have more trustable systems. When I talk to people who do forensic accounting, they offer the following heuristic. Fraud is much more likely if no one can audit a process. It's more likely someone will do something bad if they know no one can check the reasoning. They're more willing to insert a malevolent act into a system no one else can understand. And a standard optimizer that might take 10 to the 3 individuals and run them for 10 to the 3 generations, it's hard to audit a million changes to a bunch of individuals. But if I can summarize those with my data mining methods, I have a chance of having an auditable reasoning process. So we're coming to the end now. So I've said that AI will not replace programmers. There are certain tasks that a programmer does that can be better automated. And there are fantastic things we can do in the Software 2.0 model where we can automate some of the things that programmers do. But what I want to suggest to you here is that programmers do much more than programming. Programmers are the humans that understand the code, that can offer you innovations of how to take the code to some level, that can handle an emergency situation when things start breaking. Programmers do much more than programming, so even if AI totally replace programming, which it won't, programmers will still have a goal, because software engineering is the search for feedback where human software engineers and business users get together to navigate a space of options of solutions in their domain. And I think doing that navigation, building the systems, putting together the building blocks of systems using what we already do in software engineering, plus the new AI tools, is the engineering of AI systems, and that's the next challenge. We spoke in this talk about a thing called Duo, data miners being used by optimizers. You will note that many of the things I talked about have a significant automation component, and so it's right for you to ask, wouldn't Duo just be applied to itself and get rid of humans altogether? And I'm saying, well, everything I've shown you here, humans did the clever configuration of conjunctions of data miners and optimizers. And, if we do this for a couple more decades, we'll find useful cliched things that people will put together into toolkits. You can have them as one click and just run them automatically. But then what we'll have, I think, are the building blocks for the next generation of yet more complex systems that humans will be needed to respond to the challenge of putting together those yet more complex systems. I think that AI is the next software engineering challenge. I think it's human engineering, augmented with automatic methods, but humans are in there to work out how to put these things together in the best way, what to do when they break, what's completely out of the box thinking of how to do things better. So I think humans and AI do much better than just AI by themselves. And there's a whole bunch of tasks that I say are programmers' tasks, that programmers add value. Now, you might say that programmers are the backroom people and other people do the tasks that's on the screen right now, and that's not what I see in the modern agile world. My students go out and very quickly do a range of tasks across their career, including the things on the screen. Programmers aren't just programming. They're the source of expertise about the software that enable everything on the screen, that have comments on everything on the screen. So I think the right way to look at AI and software engineering is that AI has given us a whole bunch of new building blocks with which, when we apply our creativity, we can build new systems, fascinating new systems. I've offered you some insight into some of those building blocks, data miners and optimizers, but there are many other fields of AI offering many other exciting building blocks. The natural language processing people, sentiment analysis. These are whole other ways of ways we can augment current software engineering. And I think the wrong thing to do is to take all these options and put them in a blender and just run them on the cloud in some massive, great, try everything search, because that just grays everything out. I think there's much room for human creativity. Much has been done in this area. Much remains to be done. Care to join the fun? That's my question to you. So I'm Tim Menzies. I'm from NC State. We've got one of the largest software engineering groups in North America. We'd love to talk to you about your software engineering problems about this matter or any other. Thank you for your time. Any questions or comments?
Great. Well, thanks, Tim, for an excellent talk. We now have time for some questions, and we've got a few already here, but if you want to participate in the Q&A, feel free to type in your questions and send them in. So let's start with a few clarification questions. So one clarification question is about Duo. So is that a term that you yourself coined?
Yes, working with Leandro Minku and South Australians and my other grad students.
Okay, great. Another clarification question is about what do you mean by programmers? So by programmers, do you mean those who write code or also those who ensure zero defect code?
Well, I'm not seeing people having one job in their career. I'm a computer science professor. I train people for a range of tasks that they have when they finish their time with us. And so I know that programmers have to write code. And I know also programmers are the source of expertise about what's wrong with the code, how the code can be improved, what else can be done with the code. And so, I see people in agile worlds. I'm talking to middle management people that spend an awful lot of time talking to code. So I think programmers do many things. One of the things is they program, and there's many other things that they do.
Okay, great. And another question is, the talk seems to assume that programming is or will be automated. The question asker is not sure that this is true in general and asks you to elaborate.
There are many, certainly other people assume 100% automation. So I would say that the implicit complaint in this comment is true certainly of other researchers. But when we talk about optimization of learning defect predictors, we do things like we go to GitHub, and Shane does this as well. You go to GitHub, you pull down data on 10, 100, 1,000 projects, and these are projects written manually. And we try to come up with decision support systems that help you better navigate the bugs and prioritize what to do next. So I think that we can use what I'm talking about in this slide to augment automatic and human coding.
Okay, great. So another question is, what about false positives and negatives as a new class of bugs or errors in software systems?
So this is an example of anomaly detection. If you look at, I think that a learner should come with a certification envelope summarizing all the examples it's seen to date so that it can complain if something shows up. We can use data miners to detect things we haven't seen before. And when that happens, this is a perfect example of human and AI interaction, because this is the point where you wake up the Tiger team. The AI system automatically wakes up and says, I've not seen this before, help. At which point humans should be rushing in and saying, let me help you repair your self-AI.
Okay, great. So another question is about the market for AI researchers. So they feel that there is a lot of industry demand for AI researchers today, but not so much for AI-aware software engineering.
Well, perhaps that's because...
Agree? And why do you think...
No, not at all. If I go to... recently I did a paper with Tom Zimmerman at IEEE Software called Software Analytics, What's Next? And Tom offered the estimate of 1,000 people at Microsoft Redmond who have the term data scientist. Now, they're software engineers, but their job is to handle the data flow being collected from these systems. Now, I acknowledge that a lot of what I'm talking about today requires a bit of a paradigm shift, that there are textbooks to be written, there are expectations of management to be adjusted. But I'm going to predict that in 10 years' time, a lot of middle managers will be routinely asking their programmers, well, why haven't you thrown a learner or an optimizer at this?
Okay, great. So another question is, what is the danger of AI becoming an unwanted, dangerous new authority? Sounds like the Skynet comment.
Well, I'm not sure about Skynet. Personally, if I met Terminator, I'd say, oh, wow, let's talk. Wow, that's a great gun. Let's have a nice chat about that. I'd love to meet Terminator, and I think he'd be a great friend at a party. What I am more worried about is fairness. If you look at things like how large social media organizations constrain the data that it shows to us, it's really clear that we're being shown small slivers of the world that might give us a biased view. There is a whole data mining area called fairness, and now we're starting research projects where we're not just optimizing for precision and recall and minimizing false alarms, we're also optimizing for fairness, not generating models that are biased against some traditionally disenfranchised social group. So the fairness problem is a big problem, and the fairness problem can be addressed by not stopping AI, but using better AI, fairness-aware AI systems.
Great. Okay. So another question is about interpretability and explainability. So how do you think Duo relates to the current discussion on interpretability and explainability of AI systems?
That discussion is very old, and it's literally where I came in. I've been saying for a long time that we've made our reasoning unnecessarily complicated. And if you want to have humans in the loop participating in AI, if you want AI to do what it can do, which is look at lots of data, and humans to do what they can do, which is look deeply at a small number of examples, you really need interpretable models. And so we showed in this talk examples of where we prefer to put data miners into the optimizers for exactly the reason that we can have explainable systems.
Okay, great. I think that ties into the next question. So, how would you recommend syncing up high-level abstractions created by humans with AI?
Let me think of a specific example there. Like, let's say business managers have some large goal for this quarter. They want to increase their competitiveness because they're expecting some new marketplace person to come on. If that's the abstractions they're talking about, there's a lot of modeling and optimizing stuff we can say specific things for. If abstractions are things like you want to think about the composite pattern and the learner's thinking about zeros and ones, that's a whole nother story. You need some ontology mapping, and that's usually done by feature engineering during the initial modeling process. I think that's an important question. I think it's answerable, and I think we need a lot more time to answer that.
Okay, great. So another question, another comment that I'm going to try to phrase as a question is that we've seen program generation, think compilers or query by example, for ages. How is the current generation of AI-based solutions any different than the things that were supposed to replace programmers from the past?
Well, don't ask me to justify overhype about replacing programmers. The whole point of this talk is to say that is hype. If you actually look at what happens when people put together AI building blocks, there's an awful lot of human expertise in there. But if the question is this yet again another overhyped example, I point out now that we have orders of magnitude more CPU than ever before. And also, since the open source world hit, since the GitHub revolution hit, we have far more data that we can explore than ever before. I invite the questioner to go read the 30 references or read our summary paper and then make their own determination whether this is hype or actually something new and useful.
Okay, great. Another kind of clarification question is, do you also think that AI code is only a part of bigger applications with traditional coding and engineering principles mixed in?
I think that's an excellent summary of this whole talk. But what I would recommend the asker to think about is that I don't think AI can be ghettoized into a black box on the whiteboard. You know, here's the rest of the system, here's the AI component. What I've tried to suggest with this talk is that there are significant ways to combine what we call AI with there are significant ways to combine AI that changes the rest of the software system.
Okay. So I think we have time for one or two more questions. So, what are the differences between tuning AI models and tuning system configurations for performance, for example?
Well, syntactically, there isn't. If you look at the papers, if you go to my lab, if you go to the tab that says papers, the preprints thing, you'll see all our work with configuration systems, tuning a video encoder, selecting a product line for a product from a background product. Syntactically, it's the same process. There's a black box offers an opinion. There's inputs we can tickle. There's outputs that we want to minimize or maximize. That description could be held for a software process model. It could be held for a carburetor. It could be held for a configuration space, exploring, generating products from product lines. And I will say that configuration management is one of the hot topics in practical applications of AI to software engineering.
Okay, great. Well, unfortunately, that's all the time we have for today's talk. I just have a brief statement to read. So we'd like to thank Tim again for his exciting and insightful presentation and useful answers to many of the questions that were asked. A special thanks to each of you for taking time out of your day to participate in today's webinar. The webinar was recorded and will be available online in a few days at the SIGSOFT website under the Resources Webinars page. You can find announcements for upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and at www.sigsoft.org. On behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope to see you again in the future. This concludes today's webinar.